Hello, this is your Physics 101 instructor, Jerry Pinter. Welcome to our first video lecture of Physics 101. This video lecture is part 1 of the material covered in chapters 1 and 2 in your textbook. The subject of this video is motion in one dimension. This video lecture will be a combined material from chapters 1 and 2 in your textbook. These two chapters are split up into 3 parts, parts 1, 2, and 3. So today we're going to start with part 1, which is an introduction to motion. We're going to look at the graphical representation of motion, and we're going to learn about the concepts of displacement, speed, and velocity. In later videos of this chapter, we're going to see part 2 and part 3. In part 2, we'll cover uniform and non-uniform motion, and mostly we'll be talking about the concept of acceleration. And then our last part of these first 2 chapters, in part 3, we'll talk about the kinematics of falling objects. The first topic in this course on physics is called kinematics. Kinematics is the study in mathematics of motion. Motion is one of the most basic and fundamental concepts of physics. All we're going to need to study motion, to start with at least, is a unit of distance, which will be the meter. This is a meter stick here, which you might be familiar with. This gives you a general idea of the length of 1 meter. And we're going to need to measure time. And so in this course, we're going to measure time in seconds. So we have distance in meters and time in seconds. And you can see here we'll be abbreviating all of these terms. For example, a meter is abbreviated by a lowercase m. The unit of for distance, we'll abbreviate that with the letter d. And then for time, we'll abbreviate that with a lowercase t. And seconds are abbreviated with an s. One of the best ways to understand the concept of motion is by graphing the motion. So we're going to start our lecture here with a very simple demonstration of graphing motion. So let's consider we have our ladybug down here, and this ladybug is soon going to be undergoing some motion. It's going to move along this coordinate axis here. So notice we have this line here in the horizontal direction here, pointing to the right. And along the line, we have listed the distance in meters. So here is at the origin, this is called, at 0 meters here. And at 1 meter is going to be over here, 2 meters, 3 meters, and so on, all the way over here to the right at 7 meters. So what we're going to have our ladybug do is she's going to walk slowly for 15 seconds. And then she's going to stop for 10 seconds. And then after that rest, she's going to walk quickly for another 10 seconds. And we are going to basically collect some data here as she does this motion, which we're going to graph. So let's get started here. All right, so you can see here's our ladybug moving along here with the pointer here. So notice at 5 seconds, she was at 1 meter. When we get to 10 seconds right now, she's at 2 meters. And when we get to 15 seconds, she's at 3 meters. Now our ladybug is resting. So for a total of 10 seconds, she's just going to sit there at 3 meters. But now she's ready to go and she's moving more quickly. So notice every 5 seconds, she's covering 2 meters now. And finally, when we get to 35 seconds, she's done. So let's go ahead and make a graph of these points. So what we show over here is a table showing her position or her distance in meters at each 5-second interval. So for example, we know that at time 0, she started at the origin, so her distance was 0. After 5 seconds, remember, she had walked to 1 meter. After 10 seconds, she had reached 2 meters. And after 15 seconds, she had reached 3 meters. Now at that point, she waited and rested. So at 20 seconds, she was still at 3 meters. At 25 seconds, still at 3 meters, and at that point she started walking more quickly. So in the next 5 seconds, from 25 to 30 seconds, she got all the way from 3 meters to 5 meters. In other words, she covered 2 meters during that time. And then during the last 5 seconds, she also covered 2 meters. So she went from 5 meters and finished all the way over at 7 meters. So what we're going to do here now is construct a very simple basic graph. This is a graph of distance or position versus time. So one thing that's we'll have to get used to here is that we're going to plot distance in this vertical axis here, the y-axis. We're not plotting distance down here. We're showing time down here in seconds. So notice we have 5-second intervals from 0 to 35 seconds. And then our distance going vertically here on this axis starts at 0 here, and it goes all the way to 7 meters. So all we have to do is plot these points. For example, the first point is at 0, 0, which is right here. The next point is at 5 seconds and 1 meter. So that's right here. 5 seconds corresponds to 1 meter. And then 10 seconds corresponds to 2 meters. 15 seconds corresponds to 3 meters, and so on. And so in this fashion, we can plot all of these points here represented by these blue dots here on the graph, and then we can connect the dots just with a straight line, because we know that the ladybug was moving in a sort of smooth and continuous fashion, so that sort of fills in the blanks here. So this graph here now represents the ladybug's motion graphically, and we're going to learn how to interpret this graph next. So a very useful concept to describe simple motion is that of speed. In other words, how fast something goes is a good way to describe motion. And technically, speed is described as the change in distance per unit time. So what we're really doing here is we're calculating what's called the average speed. And the average speed of an object is simply the distance that the object travels in meters divided by the time that it takes to travel that distance. And time, of course, remember, is measured in seconds. So we have average speed. Our formula for calculating average speed is just d over t. So we can see that speed has units associated with it. One of the big differences between physics and math is that when you study math, you work with pure numbers. In physics, all the numbers represent physical quantities. Therefore, they have units associated with them. So for speed, we can see that we have meters on top here, and we have seconds on the bottom. We're dividing meters by second. So the units of speed are meters divided by seconds. We say meters per second. And we will rarely write this out like this. We will abbreviate the units of speed as meters per second, written as m/s. So the meaning of speed is pretty simple and basic. For example, if we have a dog, here's our dog that's running with a speed of 5 meters per second. Well, what does that mean? That means the dog runs 5 meters every second. Every second of time, the dog travels 5 meters. Now that we have a definition of speed, we can solve some basic problems that involve speed. So for example, let's say we have a student that walks 120 meters in 1 minute. Here she goes over here. What is her average speed? All right, so what we know is that speed, or average speed, is defined as distance over time. So her distance is 120 meters, we were given that, and the time is 1 minute. But remember, we're going to work with seconds for time. So 1 minute is, of course, 60 seconds. So her average speed is 120 meters divided by 60 seconds. And you can actually do this arithmetic in your head. 120 divided by 60 is just 2. So her average speed is 2 meters per second. Another variation of this problem is how far would this same student walk in 35 seconds? So far we only have one equation. That is, speed is equal to distance over time. In this case, we're trying to solve for distance. So we need to solve this equation for d. So here we have to do a little bit of simple algebra. In order to solve for d, let's get rid of this t down here. So we can multiply both sides of the equation, the left side and the right side, by t. So we get speed times t is distance divided by t times t. Now, of course, we multiplied by t to cancel this t down here. So those t's cancel out, and we're left with just d by itself. So we see that distance is equal to speed times time. So this equation here is really the same equation as we showed up here. Speed equals distance divided by time. It's just been rearranged and written in a different way. In other words, we solved for d instead of for speed. But technically, it's the same equation. So now we can plug in some numbers. We know her speed from up here was 2 meters per second. And then we have to multiply that by the time, which we were told was 35 seconds. So we have 2 meters per second times 35 seconds. And we can, again, just do this arithmetic in our head. 2 times 35 is just 70. And look what happens to our units. Here we have meters divided by seconds times seconds. So these seconds cancel each other, and we're left with just meters, which makes sense because we're solving for a distance. There's one more variation of this equation, and that is the time. So in this third problem, the question is how long would it take the student to walk 1,000 meters? So here we're trying to solve for time. So we can again start with our same equation here. Speed equals distance over time. This time we have to solve for time, t. So one way to do this, and there are a couple different ways to do it, but you can again multiply through by t. So we have speed times time equals distance, and then we can divide by speed, both sides, to solve for t. So time is equal to distance over speed. So here is a third version of our same equation that involves speed, distance, and time. In this version, we're solving it for t. So time is distance over speed, so we have 1,000 meters divided by her speed, which is, again, 2 meters per second. Remember, that was what we solved for up here. Again, we can do this in our head. 1,000 divided by 2 is 500, and in this case, it's maybe not quite as obvious, but what happens here is the meters cancel each other, and down here we had 1 over seconds, but since it's in the denominator, that flips it, and the s comes back on the top. So we have solved for time here, and as expected, we end up with a unit of time. So the time here to walk 1,000 meters is 500 seconds. Let's now take a look at something called displacement. So far, we've been just talking about pure distance. There's something called displacement that actually is a little more meaningful to us. Distance, or d, only tells us how far the object has traveled, but doesn't give us any information about the direction of travel. In other words, was the object traveling to the right, or was it traveling to the left on our axis? On the other hand, something called displacement, which is given by the symbol delta x, tells us two things. It tells us how far, in other words, the distance, but it also tells us the direction that an object has traveled. Therefore, displacement has more information, and it's a little more useful and powerful in defining motion. So let's talk about this, this notation here of delta x. So what we're talking about here is x is our x-axis here, which is in most cases we're going to consider x to be a horizontal direction pointing to the right. That's not always the case, but quite often it is. So that's what we mean by x. Delta x, you're probably familiar with this delta sign here, means a change in x. And whenever we have a delta of anything, it's always the final minus the initial. So if we have delta x, it's going to be x final minus x initial. So that little subscript there, the f, is for final, and the little subscript here, it's just like a name tag. The I is for initial. So xf represents the final position of the object, and xi represents the initial position of the object. And so what we're going to do in the next slide, we'll show some examples. We're going to be subtracting these two positions to get our displacement along this x-axis here. So let's go ahead and look at some examples. Our first example, let's say we have a man that starts at his initial position on this x-axis is at 2 meters. And so that's his x sub I. And he's going to walk along like in this direction, and he's going to end up at 6 meters right over here. So to calculate his displacement, remember what we do is delta x is equal to his final position, which is 6 meters right here, minus his initial position, which was at 2 meters. So 6 minus 2 is, of course, 4. We're going to put a plus sign there just to emphasize the fact that his displacement is positive 4 meters, meaning he moved in the positive direction, pointing to the right. So this represents his displacement. This arrow here, pointing from where he started to where he finished, represents his displacement, and we'll label that delta x. Here's another example. Let's say a woman starts at x equals 7 meters over here, and she walks to the left and finishes here at x equals 1 meter. So her displacement is, remember we do the final position first. So 1 meter minus her initial position was 7 meters. So 1 minus 7 is negative 6. So her displacement is actually negative. So what does that tell us? Well, that just means that her displacement was going in the negative direction to the left. So her displacement would be represented by this arrow pointing from where she started to where she finished. And notice the total distance she traveled was 6 meters from here to here. And the minus sign tells us that this arrow will be pointing to the left. So displacement is represented by an arrow pointing from the initial position to the final position. Displacement tells us two things. It has a size or magnitude, in this case the distance or the length of the arrow, and it also has a direction. The arrow tells us which way the displacement points. What we've just seen is our first example of what is called a vector. So displacement is a vector quantity. So what is a vector? A vector is a quantity that has both magnitude and direction. The word magnitude, you can think of that as the size of the vector. In our example with displacement, the magnitude was the length. How many meters did the man or the woman actually move? The vector, of course, also has a direction, though. Did the person move to the right or did they move to the left? And that direction is captured by the sign in front of the number. A vector is different than other quantities that you're familiar with that are called scalars. A scalar is a quantity that has only magnitude and no direction. An example of a scalar quantity is distance, right? A distance is only a length in meters. A distance does not tell us anything about direction. So in our previous example, remember we had the woman that started here at 7 meters and walked over here to 1 meter. We can write this as follows. Delta x, this is the displacement vector, is equal to negative 6 meters. Now, there's quite a bit in this notation here. So our delta sign, of course, that's part of our definition of displacement. Notice the x, there's a little arrow on top of the x. This is often used to denote a vector quantity. And the arrow in the name here always points to the right. Even though our displacement actually goes to the left, the little arrow just tells us that we are talking about a vector quantity. In this case, it's the displacement vector. The sign, remember the minus sign, told us the direction of the vector. The minus sign meant the vector pointed to the left, as shown here in the graph, going in the negative direction. The magnitude of the vector is 6. And 6 what? Well, 6 meters. So remember in physics, everything has units, including vectors. So our displacement vector carries the units of meters. So our displacement vector is negative 6 meters. The next thing we can talk about is intervals of time, the time interval delta t. So again, by definition, remember when we have anything with a delta sign in front of it, it means a change or a difference between the final value and the initial value. So delta t is defined as t sub f minus t sub I. Now what does this physically mean? Well, this is a time interval. It's the amount of time it takes for an object to get from its initial position, x sub I, at time t sub I, to its final position, x sub f, at time t sub f. So let's go through an example here which will help clarify this. Let's say we have a man that starts walking here. He's starting at position x equal 2 meters. And at this point, his stopwatch is already reading 5 seconds. So he walks over here and finally ends up at this point here at 6 meters. And he looks at his watch and his stopwatch now says 12 seconds. So let's figure out his displacement and his time interval. So the displacement, remember, he finished at 6 and he started at 2. So his displacement is 6 minus 2, which is 4 meters. All right, and it's positive 4 meters because he walked to the right and he walked a distance of 4 meters. Now the time interval, remember he stopped when his watch said 12 seconds, but he started over here when his watch said 5 seconds. All right, his watch had already been running for 5 seconds before he started walking. So the time interval for when he was walking here was 12 minus 5, or 7 seconds. All right, that just means he was walking for a total of 7 seconds. Now, in this course, time is only going to be considered a positive, a time interval is always going to be positive because time runs forward. So we won't consider time as a vector. All right, the final time will always be greater than the initial time because the clock can only run forward. We don't have a time machine, in other words. At this point, we can compare and contrast the concepts of speed and something new called velocity. So we already learned about speed. Speed is technically a scalar quantity that only tells us how fast an object is going. Remember, a scalar quantity just has a magnitude, right? It doesn't have a direction associated with it. So speed, remember, or average speed, was just distance over time. And distance, remember, is a scalar quantity. It doesn't have a direction. It's just a number of meters. It's a distance. On the other hand, what we're going to use more often in this course is something called velocity. Velocity is a vector quantity that tells us two things. It tells us how fast an object's going. That's the magnitude of the vector velocity. But velocity also tells us the direction that the object is traveling. So velocity is described as, or defined as, a displacement divided by the time interval. So velocity is delta x divided by delta t. And remember, displacement here is technically a vector. It can be positive or negative. So in other words, our velocity, we're going to find out, can also be positive or negative. This will be clarified in some examples that are coming up next. Let's go back to our graph that we made earlier. Remember the ladybug that walked along the x-axis, and we plotted her position versus time graph, and it was these data points right here. So remember, here we have her position. Now I'm writing it as x, the position along the x-axis in meters. She went from 0 here all the way up here, which represented 7 meters. And this whole thing took her 35 seconds, which is shown plotted on the x-axis here. So let's think about her velocity now. So what we're going to do here is let's just consider the first 15 seconds when she was walking from here up to from 0 to 3 meters. So remember that velocity is defined as delta x over delta t. Well, delta x, if we look at this graph here, delta x is the rise in this graph. It's how far this graph goes up because x is plotted, remember, on the vertical axis here. All right, so her displacement was 3 meters. Likewise, delta t down here is the run of the graph. Okay, in other words, the horizontal distance along this graph, which is measured in time. So one thing we see here before even putting any numbers in is that velocity on this graph is rise over run, which you'll remember from your algebra class. That's the definition of the slope of a graph. So this is one of the powerful advantages of using graphical representation of motion, is that by graphing position versus time, we can calculate velocities by calculating the slope of the graph. And we'll be looking at this a little bit further in the next few slides as well. So let's go ahead and put some numbers in now. So again, velocity is delta x over delta t. For this first 15-second period of her motion, she moved 3 meters along the x-axis, that's the rise, and this took her 15 seconds, all right? That's the run of the graph, delta t. So 3 divided by 15 is 0.2, and remember, we have meters per second, because those are our units, meters on top and seconds on the bottom. So during this first portion of the ladybug's motion, she was walking along at a velocity of 0.2 meters per second. Now we can continue by analyzing the rest of the motion of our ladybug. So remember, once she got to 3 meters right here, what did she do? Well, she just sat there and she rested for a total of 10 seconds. So notice her position here, 3 meters, stays the same at 15 seconds, at 20 seconds, and all the way up to 25 seconds. She hasn't moved. So on a position versus time graph like this, if something is standing still, it will be represented by a horizontal line. All right. In other words, the line has no slope at all. It's flat. And remember, slope is what gives us velocity. So if there's no slope, that means there's no velocity. So we can calculate her velocity mathematically. We already know what it's going to be. It's going to be 0, right? Because she's not moving. But if we think about delta x, how far did she move during this time right here? Well, she didn't move at all. So her displacement was 0 meters. Now, the time interval, delta t, was 10 seconds because she started here at 15 seconds and she didn't move, of course, but at 25 seconds, she was still there. So that's a total time interval of 10 seconds. That was how long she was just standing there. So we have 0 divided by 10 is just, of course, 0. So this is not a surprise. Her velocity while she was standing still comes out to be 0 meters per second. Now the last portion of the graph is where she started moving again, and she actually moved faster this time. Remember, every 5 seconds she covered 2 meters. So she went from 3 meters here all the way up or down the line to 5 meters here in 5 seconds. And then she went from 5 meters to 7 meters. She moved another 2 meters during the last 5 seconds of the graph. So in this portion here, we're going to calculate the slope. Now, we have to be a little careful here. Her displacement is 4 meters, okay, not 7 meters. Now, how did I get 4? Well, remember, she started here at 3 and she ended at 7. So she has moved 4 meters. That is her displacement, delta x. And how long did that take her? Well, remember again, she started here at 25 seconds and ended here at 35 seconds. So the time interval is just 10 seconds, okay, not 35 seconds. So her velocity is 4 meters divided by 10 seconds. So 4 divided by 10, you can do that in your head. It's just 0.4. And so her velocity during this last portion here was 0.4 meters per second. Now that we know how to use graphs, position versus time graph, to figure out velocity, we can also take a look at the example where the velocity is negative. So look at this graph here, which shows the motion of some object. Notice the slope here is pointing down. It's a negative slope. And so we can do a couple things here. Before we actually calculate the velocity, let's take a look at what the displacement is here. So notice at time 0, this is time down here along the horizontal axis. At time 0, we can read off the graph that this object, whatever it is, started at 4 meters. So on this graph here, which shows the x-axis drawn horizontally, we have our object starting here at 4 meters. And it looks like 10 seconds later, where is the object now? Well, it's at 0 meters. So it's gone back to the origin. So our object has actually started here and gone backwards to the left to 0 meters right here. So this is our initial position, x sub I, and this is our final position, x sub f. And our displacement is therefore -4 meters because we take final 0 minus initial, which is 4, and we get -4 meters. All right, so let's calculate our velocity here. So velocity is delta x over delta t. So we just calculated whatever the object is. The displacement was -4 meters, and the time, we can read that right off the graph, is 10 seconds. So we have -4 meters divided by 10 seconds. So this is -0.4 meters per second. So what does this mean? The negative sign, a negative velocity, just means that the object is traveling to the left. If we are assuming that going to the right is a positive direction, as shown down here, then a negative velocity means the object was moving, you can think of it as backwards or moving back towards the left. And how fast was it going? Well, it was moving to the left at 0.4 meters per second. This is our last slide of this part of the lecture, of part 1. And we'll kind of treat this like a sort of a mini conceptual quiz that you can take while you're watching this video. This puts together a lot of the concepts that we covered in this video on how to interpret motion graphs. So you can see our graph here. This is a standard position versus time graph. Position shown here, vertical axis, and time along the horizontal axis. And 3 different objects are plotted here. Object A in the red, object B in the blue, and object C has this graph or line shown here in green. So let's ask some questions here. So question number 1, where does object A start? So go ahead and pause the video now and see if you can answer this. Okay, so object A, if we look at the curve here for object A's motion, it starts here at 0 seconds. Notice it starts here at 4 meters. So that's the answer to question number 1. Question number 2 is, where does object B start? So again, pause the video and see if you can answer this question. Well, object B, here's the curve. The blue line represents object B. And notice the question is, where does it start? Well, we have to read this across the graph here, and we can see that object B actually starts at 0 meters. The question number 3 is, when does object B start moving? So again, go ahead and pause the video and see if you can figure this out. Object B, again, by looking at the graph here, we can see that it starts moving at t equals 15 seconds. So it's not really doing anything until t equals 15 seconds, and then it starts to move. The next question is number 4, which object is moving fastest? So again, pause the video and answer this question. Well, the key for velocity, remember, is the slope of the graph. So all we have to do to figure out which object is moving the fastest is look at their slopes. We don't have to do any math here. We just have to look at which line is steepest, and we can see very obviously that object B has the steepest slope, therefore it is moving the fastest. Question number 5, similar question, which object is moving slowest? So go ahead again and pause the video and answer this one. So again, using this concept of slope, which is equivalent to velocity, we are now trying to find the slowest object. So that means the object that has the least slope in its curve. And by looking at these 3 curves, we can see that object A has less slope to its line than either B or C. So A is the slowest. The last question here is, which object traveled the farthest? So again, pause the video and see if you can figure this one out. So what we're asking here is, which object has the largest displacement? At first glance, you might think that A has the most displacement because it ends up here at 7 meters, which is farthest from the origin. But notice A has only traveled 3 meters because it started at 4 and ended at 7. So by looking at this graph, we can see that object C actually traveled the farthest. Object C started at 0 and it ended at 4 meters, which is a total displacement of 4 meters. So that's the part 1 of this first chapters 1 and 2 videos. So please continue on with part 2 next. Thank you.